But David is the Tamaki Endowed Chair of Atmospheric Sciences at the University of Washington. He did his undergraduate in physics at University of Massachusetts, and then a master's in oceanography at the University of Washington, then a PhD in atmospheric sciences at the University of Washington, did a short stint as faculty at University of Wisconsin, and then back to the University of Washington, where he's been ever since. During his time there, he's had many different roles. Previously, he was head of the Joint Institute for the Study of the Atmosphere and Ocean, or the director for a time, as well as UW's Earth Initiative. He's served on numerous international science panels, on committees of the National Research Council. He served for 5 years as co-chair of the Science Steering Committee for the U.S. Program on Climate, and is co-author of several international science plans. He has published over 100 papers in peer-reviewed journals, both in atmospheric sciences and oceanography, and has been twice awarded Distinguished Teaching Awards. And much of his research is really focused on understanding the interactions between the atmosphere and the ocean, sea ice, topography, but essentially the interactions between the atmosphere and the Earth's surface and the variability in the atmosphere that might drive. So today he'll talk to us about various parts of the climate change and food security. So with that, I'll turn the time over to David.
Let's stand behind here. This is not my way of doing it, but if you see me wandering, someone just go like this so I come back here. Yeah, perfect. So actually, before we get started, who was here last week? Jonathan Lynch, right? Can someone just really briefly, like in 1 minute, summarize and tell me what he said?
Manganese matters.
Manganese matters. Okay. Oh, he was really down into the chemistry of plant production.
Yeah, he was talking about the possible effects of temperature change on soil chemistry and how plants will change what they're taking out of the soil.
Okay, great. So yeah, plant uptake of nutrients based on temperature changes and how it affects soil productivity, biogeochemistry. Okay, good. I'm just going to touch very briefly on that, but there's more players than that in terms of crops in particular, and that's going to be my focus today. So these are just fun facts to know. A couple of critical things here. 40% of the world's food production comes from 20% of the land in the world that's irrigated. Rate of change, the greatest rate of change of global food production in the history of mankind is this 20-year period, 1960, 1980, called the Green Revolution, where food production went up 2% per year, in equal parts due to better varieties, dwarf plants actually, that could actually withstand heavier grain on top and not fall over. It's called lodging. If it falls over, the plant's dead and you don't get any grain out of it. So there's smaller varieties, increased irrigation, and cheap nutrients that came about from cheap power in machinery, basically, and a new technique of developing nitrogen. So that was 2% per year for a 20-year period. The rate of increase of grain production peaked in 1975 and it's been decreasing ever since. It's now less than about 0.5% per year is what it's increasing at. Soil loss is 15 million hectares per year. That is the amount of soil that's being lost each year due to wind erosion, water erosion. This is soil that is less productive than it used to be. And also salinization is another one. About a quarter of the arable land in the U.S. is now, in the world, is now classified as degraded, right? So producing less than it used to produce. All this comes at a time when the estimates of the need for food production are expected to double in the next 35 years, right? So if you work that out, that's more than 2% per year for a 35-year period, which is about twice the rate, about twice the lasting of the Green Revolution. Now, there's a slide here I was going to show you. Maybe show you. That's me. Okay, so it's a little dark. Okay, so land, we already summarized. Land used to, in fact, up till 1960, actually, most of the increase in food production was due to the fact you just got more land, plowed up more forest, put more land in. 1960 to 1980 was this green revolution period. And like I said, water, new varieties, and cheap energy, basically. And energy, it's cheap right now, but it's not going to stay cheap for long. Nutrients, nitrogen is now produced by this chemical process, but actually phosphorus is an important nutrient. The estimates of how much phosphorus is left vary anywhere between 30 years and 250 years, right? So phosphorus is increasingly becoming the limiting nutrient. And then you have climate change, and that's what I know most about, and I'm going to spend most of my time talking about that, okay, today. So 3 parts. One slide is just talk about where the food insecure live today. The second part, we'll talk about projections of what's going to happen over the next 100 years due to human activity. And the third part will be just focused on based on what we know for sure from the climate change perspective, the science that can deliver. What do we know about what that implies about global food production? Stop me at any time. Ask all the questions you want, okay? I can throw some stuff out. If we don't get to it, it's no big deal. So where do the food insecure live? This is a map of the colored countries here. Don't worry about why they're colored differently. But those are the countries where the 1 billion people in the world live today that are malnourished. So 1 out of 7 people today in the world is malnourished, don't get enough food to live basically a healthy lifestyle, right? They eat a variety of things, but rice, wheat, and maize constitute about 50% of the calories. And if you notice one thing about this, which I guess I'll point, all these people live basically between 35 degrees north and 35 degrees south. Why those matter is because that's in the tropical dynamics, in climate dynamics, that's the region we call tropics and subtropics. And it's important because those regions are special. The temperature is relatively steady and hot, okay? So that's where they live. They depend heavily for agriculture for both food and income. It turns out that most people in agriculture don't grow food for themselves. They're actually growing food for somebody else. They make an income and they buy food. Okay, so, oops, nothing's happening. Okay, so what are the projections of climate change? I'm just going to focus on the things that the climate community has deemed very likely. That is, there's a greater than 90% chance that this is going to occur based on quantitative analysis and an elicitation of the expert view. So this is a combination of a real statistical analysis and just talking to people who are experts in climate and saying, like, what are the odds, basically, right? All right. So what's going to happen? God, I like roaming, and this is really constraining. Okay, so what's going to happen depends on 2 things. I'm going to have to roam in a second. One is just on how much carbon dioxide are we going to put in the atmosphere. I mean, there's other greenhouse gases as well, but carbon dioxide is by far the most important one in terms of human changes. And how much is going to go in is not a climate question. That's a society question. It depends on population growth. It depends on choices of energy that are used, whether you're fossil fuel or renewables. It depends on things like global governance, governance choices, global versus regional. It depends on the priorities of environment versus other things, okay? But we can do this calculation, and the way this is actually done is oil people, energy people, demographers, political scientists all get in rooms and they come up with these different scenarios for choices of energy use and how things will play out in the future. But we can actually do this conservative calculation pretty simple in our heads, right? And I think it's important to do that because then then it's not kind of a black box. So let's say the world population increases from 7 billion today to 9.5 billion. That's a third increase in the population. Now that's kind of the projections from the UN, and those projections have been slightly going up over the last 15 years, but they're pretty steady. So let's say we increase the world's population by 33%, a third, between now and 2050, 35 years from now. Let's say we do that and everybody in the world develops, which we want, right? We want people who are kind of poor and on the edge to develop, anytime you develop, you use more energy. You live at a higher life standard, you use more energy. And let's say we do that, right? The 3 billion people in the world that are kind of at the poverty line or below, and we add another 2.5 billion, and they all develop, and they all use a lot more energy. And we do it without increasing the carbon dioxide emissions. What are the odds? 0, right? Pretty slim. Okay. So good. So we have a pretty conservative estimate of what will happen, and we know the answer, because today there's 400 parts per million of CO2 in the atmosphere. That means if I grab 1 million molecules here of air, well, say if we were outside and we did this, and I just counted them, 400 would be carbon dioxide, and the rest of them would be other things, mostly nitrogen, right? And then second, oxygen. Okay, today we're increasing, because of emissions of carbon dioxide, mostly due to burning of fossil fuels, we're increasing it 2 per year. That is 400 today, we're increasing it 2 parts per million per year, right? If we go from now to the end of the century, it's 85 years. So how much do we increase? 170, right? 2 times 85, 170. We're at 400 today, so we get to 570, right? So that's twice pre-industrial, right? And that's a pretty conservative estimate based on assuming that we add these 2.5 billion people and they all develop, use more energy, and there's no increase in CO2. So that's what we've done here. We come up with, 570. So here's what the experts tell you, right? All these different emission scenarios. Each one of these lines is for a different assumption about what fossil fuels are used. I'm not going to go into all the details, but let me describe you 3. 1, so there we are today, 2015, and we're at 400 parts per million. And these are projections, and each one of these projections assumes different things about politics, about energy choices, population growth, et cetera. A2 is called business as usual, because basically it's a world where all nations move at a different rate towards renewable energy, some fast, some slow. It's a world of slowly converging global policies. Environment is a priority, but not the priority. So there's a transition from fossil fuels to renewables at different rates in different places. It's basically today. It's the world that if you listen to all the details of these scenarios, you'd hear today. That world takes you to the end of the century to 830 parts per million, right? Now this world, B1 here, so this is called business as usual. B1 is a world where population peaks at 2050 and declines. Environment is the priority. Global governance is the way you do it. Regulation, right? What else? You rapidly move away from a consumer society to basically a more sustainable, low consumption, global economy, right? Does it sound like a world you know? Right? So I call that one utopia. That's my word for it, right? Okay? Just because, it's not going to happen. Not because it's the ideal, it's just because the ideal never happens, right? So that's utopia. And let's just split the difference. It's like somewhere in between these two, and it takes you to about 700, right? So actually, I should say, utopia takes you to about 530, which is this calculation we just did, right? So you can see how kind of unreasonable that is, in the sense that it's really, if you wanted to get to 570, it'd be quite draconian. How draconian is here. If you wanted to stabilize carbon dioxide in the atmosphere, so humans are burning fossil fuels and they're putting energy in. Nature, the carbon cycle, will slowly take this out. Some of it gets dissolved in the ocean. Eventually, increasing CO2 makes the climate warmer. You get rainfall, you get rocks that are eroding, and that will slowly take carbon dioxide out. But that's a pretty slow, both of those are pretty slow processes. So if you wanted to just sort of keep on putting stuff in and have nature take it out so there's an equilibrium, so the carbon dioxide doesn't change, you actually have to get it down to an average emissions per person of 100 kilograms per person worldwide. The US today averages 5,500 kilograms per person, right? So this is why this problem is so contentious. It's not because of the climate. As I'm going to tell you in a second, the answer of what happens when you increase carbon dioxide was first calculated in 1896, 125 years ago or something like that. Why it's contentious is you basically have to get down the fossil fuel burning from today to 2% of today, which means you either have to scrub the CO2 out of the atmosphere, which is incredibly expensive, or you have to rapidly move to renewable energy. It's hard, right? Okay. So if you believe it's a problem, it's a real big problem. Okay? Everyone get that? It's important to recognize this. I mean, it's important to recognize if you believe this is a problem, the fixes are not, oh, I'm just going to turn off the lights when I leave the room every time, right? The fixes are you don't use fossil fuels, or you use them and you scrub CO2 out of the atmosphere, which is expensive. Okay, so these assessment reports come out, and all I'm going to do is focus on stuff that the global community of climate scientists is, kind of summarized and agreed upon, that we're quite confident in, right? So these assessment reports called the IPCC, they come out about every 6 or 7 years. There was one in 2007 called Assessment Report 4. There was one in 2013, a year and a half ago, called Assessment Report 5. This business as usual scenario used to be called A2. It's now called RCP 8.5. Don't worry about why. The effective carbon dioxide. So you have carbon dioxide, you also have methane and nitrous oxides, all increasing because of human activity. Carbon dioxide is the leading one, but if you include all the other things, it's an effective carbon dioxide of about 930 parts per million. If you do that, the kind of average across all the climate models is that the global average temperature will increase 3.4 degrees Celsius. Okay? Now, utopia used to be called B1, now it's called RCP 4.5, gets you to 530 parts per million and a 1.8 degrees C global increase in temperature. And then split the difference, and I'm just going to focus today on split the difference. Kind of optimistic, but also a little bit realistic. Now it's called RCP 8.6. You get 670 parts per million at the end of this century, and a 2.8 degrees C temperature increase. Now, it turns out that given the same exact carbon profile into the future, what's going to happen, if you give it to this whole host of climate models, they'll all give you a different answer, right? So you have two uncertainties here. One is how much carbon dioxide is going to go in the atmosphere. The other is what's the response to that carbon dioxide. I'm just going to show you, there's going to be patterns that show up here. These patterns, no matter, so the global average temperature of each climate model would be different, but the pattern is the same, right? And that's really important. It means we have a lot of confidence in the pattern of change. It's just the amplitude we're not quite sure of. We also have high confidence in the pattern of precipitation change. So we have high confidence in the pattern of temperature change and precipitation change. I'll show you what they are. Now, if the nice thing is that since that pattern is the same across all models, if you're an optimist, everything I'm going to show you today, just multiply by 0.7 and you'll have the answer. If you're a pessimist, just multiply everything by 1.2 because the pattern is the same, okay? And we understand why that pattern is the same. I'm not going to go into it today, but we do. Okay, so if you swap this vocabulary for these emission scenarios, the results and the conclusions from 2007 are the same as they are from 2013. Not a surprise. It's an old problem, okay? This latest assessment adds one more emission scenario to illustrate that it's virtually impossible to keep the global average temperature increase below 2 degrees this century, okay? Why that's significant is that a lot of mainstream economists have come out and said 2 degrees C is too dangerous to exceed, right? So there's a big push actually to cut emissions not because climate scientists say it's dangerous, but because a lot of mainstream economists say that this is too dangerous. There's a flip side of this. I don't know if anyone's seen the papers in the last week or so. There was one I think in Salt Lake paper about geoengineering, right? Purposeful manipulation of climate to try to keep it below this temperature. That's extremely dangerous. I could give a whole talk on that. It's the scariest thing that I've heard about in my life, actually. No, really, I was at a meeting, this is a side. I was at a meeting once, and it was called the, no, you can ask me the question and answer. Okay. But otherwise, there's really nothing new. Everything that was in the AR5 report was in the AR4 report. And if you're a policy person or if you're the public, there's nothing new in this report. So all the things that were said 6 years ago were the same thing that were said actually 16 years ago, which are the same things that were said 3 years ago. So no changes, which is nice. So how much carbon dioxide is in the atmosphere and how much will there be? This is 40,000 years ago. This is today. And you can see this is bops up and down. The scale got removed somehow, but it's bopping up and down. Oh no, here it is. From 280 parts per million to 200, 280, 200, 280, 200, 280, 200, 280, 280. Here's 380. This was about 10 years ago. And now today we're at 400. Okay. These things, anyone know what they're called? Don't say it if you're a geologist. What is it called? When you go from here to here, what do? It's Ice Age, right? You come back up here and it looks more like today, Ice Age. So these things are bopping back and forth, and we know this because this is measured from gas bubbles trapped in the ice in Antarctica and Greenland. You just go down, count the number of layers so you know how old you are, take out the bubbles, measure the CO2 concentration, right? So it's a straightforward measurement of what the atmospheric CO2 concentration was. So here we are in 2100, right? So we're definitely out of bounds from the last 40,000 years. Probably, oh, come on up, okay? So the most conservative estimates are that we'll double CO2 from pre-industrial, 280, right? 280 doubling is 560, right? That's that idealized calculation we did, right? Estimates in this split the difference thing are up here at 670, right? More realistic scenarios then almost triple carbon dioxide from pre-industrial. It's more than any time in the last 3 million years. So CO2 is going to be higher than any time in the last 3 million years, probably any time in the last 30 million years, although we don't have really good constraints on that data. The rate of change is about 100 to 1,000 times faster than nature. So if you look at the historical record here, the biggest change you see is 100 parts per million in about a 10,000 year period, right? We're going to go 300 in 100 years, right? So that's a lot faster. The time it takes to reach normal levels, if we just stop emitting everything today, we emit no more carbon dioxide, is several thousand years, right? So nature takes a long time to clean this up on its own. Okay, so if we do increase CO2, what's going to happen? What's shown in the black line here is the observed global average temperature. So averaging over all the globe over 1 year, and you just do that from 1990 to 2000 here. It's the observed global average temperature for this 100-year period. It's increased 0.85 degrees Celsius. Remember that number, 0.85 in 100 years, okay? Sounds like a small number, right? It is a small number, okay? Now, it's a small number, but the difference between glacial conditions, where you had 3 kilometers of ice, and today is like 3.5, right? So 0.85 isn't that small, right? When you think about it, when you think about the climate changes locally that go on when you do that. What's shown here in the gray is every climate model moving forward forced by the observed increase in CO2 over that time period. Now, if you do that with every climate model, they'll all warm, but they all warm at a different rate. So what they've done here is they said, let's assume we start all at the same place in 2000, we went backwards. What would be the spread across the climate models? How uncertain it is? Well, the answer is the average across all the climate models also increases 0.85 degrees C, but there's some uncertainty here. One increases it, 1 degree over the course of the century. Another one increases only 0.4 degrees over the course of the century, right? Now, moving forward, so that's uncertainty. That's they all have the same exact carbon dioxide, but they all have a different response. Some warm more than others. Okay. Now, moving forward, let's just concentrate on this green line. That's what happens under the split the difference between utopia and business as usual, right? And we go from here to here. This is a 2.8 degree rise over this century, right? Which is about 3 or 4 times, 3.5 times what we had last century. And that's the average overall climate models, but you can see there's a spread here. Some climate models give you less warming, some give you more warming, right? So every climate model has a different answer at the end of the day, even if they're given the same carbon dioxide emission scenario. For utopia, right, the average across the models is about 1.8, but there's some spread. And for business as usual, it's up here at 3.6, it looks like, with some spread. This is an interesting one. This is if we stop emitting today entirely, right today, temperatures will still increase another 0.5 degree over the course of this century, just because the system is not in equilibrium yet. The ocean's still cold and still absorbing energy, and until it warms up to be an energy balance, the system is not in equilibrium, right? So we've already bought another 0.5 degree of warming, even if we don't put another CO2 molecule in the atmosphere. Okay. Any other questions on that one? Yeah.
Why does it even out after?
It evens out because the assumption is that the emissions of carbon dioxide are going to really come down a lot. So the assumptions here, that's a great question. This thing, because the assumption in this one is that actually we're emitting less, a lot less in 2200 than we are today. Right? That's the way it goes. Okay. So if you put that into perspective, so here's the 0.85 degrees over the 20th century. Here's what we go into the future. Each one of these lines is for a different emission scenario. And the spread, for example, this one here, A1B, right, it's about 2.8 degrees. But one climate model said 2.2. Another one said 3.8, right? So there's a big spread across the models, uncertainty in the models. If you go backwards in time, you start run out of instruments, and this all comes from tree rings and corals and other proxy data for and actually this is northern hemisphere average temperature. And you can see it bounces around here, and the gray is kind of like the uncertainty. And the thing to point out is basically we're way out of bounds compared to at least the last 1,000 years, right? Compared to anything experienced in the last 1,000 years. Okay. Yeah. So at the end of the day, you have kind of almost equal uncertainty between how much CO2 is going to be put in, so there's an uncertainty there, and what's the response going to be, what the model response is to the same emission scenario. The uncertainty and the projections of the future are about equally split. Now, nobody lives on the global average temperature, or very few people do, right? So this is a map of if you do have this middle of the range, say take the middle of the range climate model in terms of its response to increasing 2, and you take this kind of split the difference emission scenario, this is what the global average temperature change, the global temperature change would look like at the end of the century compared to the end of last century. Purple is 7, red is somewhere between 2 and 5, depending on the color of red. And kind of light green here is about 0.5, right? So even for the same emission scenario, a very sensitive model will give you a much larger warming than this, but the pattern is the same across all the models. So what do you see in this pattern? Warming over the continents versus over the ocean. Same? More over the continents, right? So the global average is 2.8, but the continents get more warming than the ocean, right? And where's the warming the most? The Arctic. How come? Oh, this is a trick question. There's a intuitive answer, and that's basically you melt ice, right, and you replace it with land or ocean, and it's darker and absorbs more energy. But in fact, most of the warming is in winter when there is no sunlight to reflect ice, right? So most of the reason here is because you melt ice and replace ice with ocean, and from the atmosphere point of view, ocean looks like ocean, but ice looks like land. And in the wintertime, it just cools down like a rock. So most of this is just because you're just adding more ocean to the northern hemisphere as far as the atmosphere is concerned. Okay. So, and the numbers here are typically 3.5, 4 degrees over land areas. Okay, now, again, if you're an optimist, multiply by 0.7. If you're a pessimist, multiply by 1.2. And you got roughly the answer. Okay. So what happens to precipitation? Well, anywhere where it's blue here, it's wetter, more rainfall. Anywhere it's red, there's less rainfall. The colors tell you the amplitude of the rainfall, but more important on this plot is the stippling, right? The stippling tell you, I can never describe this. If this is today's amount of precipitation and the average across all the models says it's going to increase by this much, okay? The stippling tells you that the spread among the models is smaller than the average change, okay? Is that okay with everyone? I can never say this right. So the stippling tells you the places where the model spread is smaller than the change predicted, the average change predicted across all the models, right? So where we're confident is in high latitudes here, and this is simply because as you increase the temperature of the planet, Clausius Clapeyron tells you increase the water vapor. So if I have the same storm coming in lifting water, but there's more water vapor, I get more rainfall. So this is mostly changes in winter rainfall here, increased winter rainfall in the high latitudes of both hemispheres. What's going on here is a little bit more complicated to explain, but there's a lot of confidence that basically as you increase temperature, the Hadley circulations expand, right? And so the jets move poleward, and so where this precipitation is falling is moving poleward, and that leaves the subtropical regions drier. And this happens in almost all the climate models. So places where all the climate models say it's going to dry, well, you know, there's a lot of stuff over here at the ocean where no one's lived, so let's not worry about that. But, well, yeah, unless you're a fish, I suppose. But let's say like Central America, that's a place where all the climate models tell you you're going to dry. And the difference between the climate models is the average change is actually very large compared to the difference between climate models. Southern Europe is one of those places. Southern Africa. Yeah, not much else. There's not a lot you can say about precipitation. I should point out that here's a place where all the climate models tell you it's going to rain more. But it's also a place where the climate models are terrible to start with, right? So anyone know anything about the rains in this region? There's short rains and long rains, right? Climate models actually put the rains in the dry season, in the dry season, in the rainy season. So given that you start really, really in a different world in this place, you probably shouldn't trust the answer. Okay? All right, so there's not much we can say about rain, except that in the high latitudes it gets wetter, and in certain regions here and here, it gets drier in terms of precipitation. Okay, so what does that mean for food security? Okay, so I'll show first what little you can say about precipitation. And I should say the very first meeting I went to on this was, remember the first slide that had this beautiful Arctic scene with this kind of angular building? That's the Global Seed Bank in Svalbard, Norway. That was built for two reasons. One is to be a backup seed bank for all the seed banks in the world. And the other was to collect and preserve seeds that might be needed in a climate change world, in a different world. And so one of the objectives they had was, what is the world going to look like? So what seeds should we go out and look at, right? So my job was to tell them what the world was going to look like. I came to this talk prepared to talk about precipitation because growing in upstate New York, I knew that precipitation was everything. Okay, we'll come back to that. Turns out I was wrong again, okay? Okay, so precipitation, oh, this didn't come out too good. This looks all like black. It's not all black. It's not as black as that, but this is everyone see this? This is Southern Europe. Here's Norway up here, right? This is winter, this is summer. If this showed up clear, you would see there would be around a 30 to 40% decrease in rainfall in this region in wintertime, which is their wet season in this region. And the same decrease here in summer, but it doesn't rain much in summer, so it's mostly dominated by this. So averaged over the year, you're looking at about a 20 to 40% reduction in the precipitation in these regions. And the models all agree on this. Okay. Anyone know what the decade-long change in precipitation was during the Dust Bowl? Let's vote. 100%, well, 100%, that means no rain. 50%, 25%, 7%, 1%. Takers for 100? Huh? 10? 10? It's 7, right? So this is like 4 times the Dust Bowl deficit. And it's a permanent deficit, right? This is what the average year is going to look like at the end of this century. And the models agree on this, right? And we understand the physics. So you can actually go into the record and say, well, what would happen if we actually had a 30% reduction in the precipitation in this region? Here's this kind of Central Asia region, all the stands, right? Iran, Pakistan, Afghanistan, Tajikistan, right? 30% reduction in rainfall for about a 4-year period. And if you look here, here we go. What happened? Well, in Iran, 80% of the livestock was lost. 35 to 75% of the reduction in the wheat and barley. 40% of the livestock lost in Afghanistan. 50% of livestock in Pakistan. 50% of the grain crop lost in Tajikistan, right? So anyone know how livestock are done in this region? Like, why did so many livestock die? So you don't get out your tractor, bale up a bunch of hay, put it in the barn, and feed your cows, right? You're grazing, right? So the health of the grazing field tanks when you have a 30% reduction in rainfall for 4 years, right? So pretty much this is a region where you kind of have to give up livestock. And if you know about the culture of these regions, livestock is really important, both in terms of people's perception of wealth and actual wealth, and working animals and food production. So by the end of the century, similar water stress in agriculture will be the norm throughout the tropics and subtropics due to the changes associated with increasing CO2. And that's kind of hard to get around. But after that, you can't say very much about precipitation changes. Okay, where am I going next? Temperature. Okay, so I came to this meeting I was telling you about, and I came with all these slides, the few slides I could muster, about how changes in precipitation would affect food production, because I knew that temperature was precipitation was the answer. And the first day of this meeting was the geneticist and the seed bank people, and they were all, and the agronomists, and they were all talking about temperature. They were excited to see each other. They worked together a lot, and they were all talking about temperature. And I thought, this is really strange. Like, why worry about temperature? And so the person sitting next to me was an economist, said, gee, do you think you can kind of give an idea of like, and I wish I could draw something here, but just a second. Okay, here's one axis, right? Here's another axis. This is just change in temperature along here, and this is be normal, right? So if this is normal, and this is the change in temperature, I could just plot like a histogram of summertime temperature. Well, normal is the most likely case, right? So basically this graph looks like a Gaussian, like a bell curve, right? And there's some normal here, and then there's really cold, and there's really warm. So she drew this thing, and she goes, do you think you can tell them what it looks like in the future? Does it look like this is just shifted a little bit? Or does it look like this is here, and the future is here, and there's no overlap? I said, well, yeah, that's really easy. That's something that I had to know before I even went to graduate school. Because if you know what the average temperature change is, you can just build that histogram by grabbing some data on the web. Well, there's no web when I went to graduate school, but you get the idea. It's really a simple thing to do. And so I did it. I went back to my room. I threw away all these precipitation plots, and I just came back with a bunch of histograms. And I'm going to show you the histograms. I showed them right now. So first, we need one thing. That's how does the growing season average temperature change? It turns out here's summer northern hemisphere, but if you did summer southern hemisphere, you'd just be the same. Any 3-month period looks the same. And again, over land areas, we're looking at the average, this sort of growing season average temperature change of somewhere around 3 or 4, maybe even 5 degrees by the end of this century. Right? What was the answer for last century? Less than 1, right? Okay, so we're looking at 3, 4, maybe even more than 4, okay, averaged over the growing season. And again, nature's done this experiment for us, right? So here's France, 2003, heat wave, extremely heat wave. The average summer temperature was 3.6 degrees above normal. So a lot of people died in France and Italy. In Italy, there was a 3rd drop in the maize production, There was a 30% decrease in maize and fodder production. Fodder production is just producing food for animals instead of people. 25% decline in the fruit harvest and a 21% reduction in wheat yields. So by 2100, you have similar temperatures. This will be normal. I mean, this is what the projection is, between 3 and 4 degrees growing season average temperature, and you're looking at a third drop in yield, right? So let's go to this histogram. Here's France. And here's a normal. So this is the summer average temperature, the growing season average temperature. Here's normal, 0. Okay, it's departure from normal. Here's the coldest summer on record. It's a little over 2 degrees colder than normal. Here was the warmest on record up to 2003, which was about a little over 2 degrees warmer than normal. And here's 2003 at 3.6, right? So it's really out of bounds. And those changes in France, if they were due to precipitation deficits, you'd expect that change every 3 years. There was nothing special about the rainfall that year. It was all temperature. Okay, so if you look at France and you say, okay, I'm going to assume I have the same year-to-year variability. Most of that's natural variability. There's a little bit of climate change in there, but probably not much, because it's, you know, the global average temperature hasn't increased very much because we haven't increased CO2 that much yet, okay? But I'm just going to take the same year-to-year variability, and I'm just going to add the projected average change to France. And I did this in every climate model, and I just said, I'm going to take all of the summers projected by all of the climate models, and I'm going to make another histogram like that and say, what are the odds in the future? What do they look like? Okay, and the answer is that. Okay? So what are the odds that the temperature in the future, okay, I'm going to have to go over here. 2003 is right here. What are the odds the temperature at the end of the century in France will be higher than the highest temperature ever recorded in France? Really good. Really good. How good? Roughly. Roughly. 50%. Yeah? Pretty good. There's a little chance, a tiny chance, it's going to look like normal. And there's a tiny chance it's going to be 10 degrees C above normal. Of course, 10 degrees C above normal puts you smack in the middle of the Sahara Desert today, right? That's a big change. Okay, now you can do this for other places. Here's one for the Sahel, tropical Africa. Tropics is really famous for being steady temperatures, right? So here's the record from last century. A really cold summer is about half a degree colder than normal, and a really warm summer is about 0.75 degrees warmer than normal. And here's the future. And what are the odds that the temperature at the end of the century is going to exceed the highest temperature ever seen in the Sahel? 99%. There's no overlap in those graphs, right? I mean, there's tiny tails that probably overlap at some point, but it's basically, you know, the odds are pretty much 100%. Now, I could do this for every place in space. Show you a picture. I won't bore you with that. I'm just going to show you a map. And the map is going to say, what are the odds that your place in space, the temperature will exceed, given this split the difference emission scenario, right? This is not the business as usual. Given the full range of climate models from being the least sensitive to the most sensitive, what are the odds that the temperature at your place in space will exceed the highest temperature ever seen at your place in space? And that's the map. And red is greater than 90%, right? So pretty much all of Africa, a lot of Southeast Asia, a lot of Central Asia, Spain, a lot of the Southwest U.S., right? A lot of the East Coast U.S. A lot of the world is a very different world, right? Not experienced, at least in the last 100, since we've been having instrumental records, okay? There's something that looks funny about this graph. If you go way up here, it's only about 50-50. How come? There's so much variability, right? The mean changes are largest in the high latitudes, but the variability is also really, really large. So you have to wait longer. And this has actually been known since a paper was published in 1970, that if you want to see climate change, you look in the, even though the changes are smallest in the tropics, the signal is easiest to see in the tropics. All right. Okay. Okay, good. So by the end of the century, it's very likely, greater than 90% chance that the the temperature in the tropics will exceed the highest temperature ever seen in the tropics and subtropics. Okay. Now, maybe, what does that mean about, this is where I was surprised. So at this meeting, these guys were showing data like this. This is a plot of Iñaki Valley, northwest Mexico, the home of the green revolution for wheat. This is irrigated. This is way too much pesticides, way too much herbicides, way too much nitrogen, right? So there's nothing limiting these crops at all. And this is just a plot of nighttime temperature versus yield. And each one of these dots is one season. And you can see basically as the temperature goes up, yield goes down. The slope of this line is 10%, right? So it's a 10% loss of yield for every degree C temperature you increase. There's nothing limiting this graph. This is all temperature. This was a complete surprise to me. If you do the same thing, okay, well, let me get that a second. So why? Well, there's a bunch of reasons why it turns out. It turns out that, one, when grain grows, the spikelets at the end are less fertile under higher temperature. And the spikelets are the thing that grows out the grain. It also turns out under higher temperature, the plants grow faster and they stop growing. And so this is a well-known thing that they stop growing. So the grain starts to grow and it stops growing earlier, which means the total amount of grain in the head is less under higher temperatures. You also end up with higher water stress just because the plant is hotter and it's bleeding water to do that. And then you have increased respiration. And depending on who you talk to and what grain you're talking about, they'll say that one of these things is more important than the other. But the bottom line is this collection of processes means for a 10% reduction in yield under idealized conditions. Plenty of water, plenty of nutrients, too much pesticides and herbicides, right? You do the same thing in the Philippines with rice, you get 17% decrease per 1 degree C increase. If you do the same thing in India, the Indian wheat breeder had 15% decrease for every 1 degree C increase. On optimal conditions otherwise, right? Okay. I'll come back. I didn't know this, right? So this was a surprise to me. And I gave this talk, and without this, I just gave them the histograms. And, I waited, and at the end, and it's like, no one really said anything. I thought, oh, I missed the boat. Now, I didn't understand what they needed, or maybe I just didn't explain myself well. And then Kerry, the guy who runs the seed bank, stood up and he said, we got to completely rethink what we're doing, right? This is something that is a take-home. I mean, all climate models would do this. In fact, Arrhenius in 1896 would have come up with the same answer. He just didn't know what the impacts were on the crops, okay? So it's important for all crops, but especially for wheat, rice, and soybeans. These are the crops that would otherwise benefit from just increasing CO2 because of food, and maize. Okay, so, okay. There we go. Why does it, there we go. So the impacts of climate change on food security. One is you have just increased temperature, and under otherwise optimal condition, you expect at least a 10% decrease per 1 degree C warming. How much warming do we have by the end of the century? 3 or 4, right? So we're looking at 30 to 40% reduction in the major grains, right? By the end of the century under otherwise optimal conditions. Of course, we have less than optimal conditions, right? So that would be true in India, Southern Africa, Middle East, anywhere in the tropics and subtropics where it turns out you're beyond the optimal temperature for growing grains. And I'll come back to this. Increased volatility in crop yields in the mid-latitudes. So this is pretty new. I should have realized this actually at the time. And actually this is why in upstate New York we didn't care about temperature. And I didn't. Actually, I didn't realize it until about 9 months ago. Well, maybe more than 9 months ago, but within the last 2 years. So people have been focused on the tropics for a long time. They know that climate change in terms of food production in the tropics is a really big deal, right? But it's also true it's a big deal in the mid-latitudes. And this is the reason why. And this is why it is growing up in upstate New York, we didn't see this. Here's a typical idealized curve. And this would be, in biology, this would be called fitness on on the y-axis, and on this axis would be temperature, right? Have people seen this kind of plot before? Only in this case, I put relative yield, relative to like the perfect amount of yield you can get, right? And they typically look like this. Well, you're near an optimal temperature, that's the best yield you can get. As you get colder, it's less optimal. As you get warmer, and these things are almost always shaped like this. They're kind of like a inverse Planck curve, if you're from physics, right? Where they just fall off fast at this end. Okay, so here we are. If this is the average temperature, and you just have natural variability bopping you back and forth here, and if you just look up here and you just plot this thing, you find out that the yield goes from here up to here and then down to here, right? So that the range in the yield goes from perfect to 10% reduction. Not a big deal. That's upstate New York. That's Iowa. That's France. That's China. That's Ukraine today, right? We're really right on the optimal for wheat, maize, what am I missing? Soy, okay? Okay, so when it was really cold in upstate New York, we had a little bit of reduction in yield. When it's really warm, we had a little bit of a reduction in yield, but we didn't really see it. It's mostly rain. If you had a really dry year, bad. If you had a too wet year, bad, right? So we cared about rain. But now let's just add, let's say the same natural variability, and we're just going to shift the temperature to be slightly warmer due to global warming, and you're out here. Now yield goes from, well, perfect to 0, right? Right? And we know these slopes. I mean, these are measured in these agricultural plots around the world, right? So what happens in the mid-latitudes is, yeah, maybe the mean yield might be up here somewhere, but the volatility from year to year is going to be massive. And this is not because the climate change is becoming more volatile. It's because the climate change, the variability from year to year is the same. It's just shifted, right? And so that the volatility in the yield production goes through the roof. Like how much so? Well, this is a plot of yield anomaly relative to the average today. And the average is here at 0, right? And the blue line is today. And so it says basically what's the likelihood you'll be near average? Well, it's pretty high, right? There's actually more likelihood you'll be a little bit above average because we're actually a little bit below the average today in the United States. Just a little bit for maize anyway. And there's a slight chance, a very slight chance, it'll be a 10% reduction. Now, if I just add a 2-degree warming to that and have the same variability, well, now the average goes down, but look at the possibilities now, right? Now there's a slight chance you'll have a 40% reduction, right? There's a slight chance you'll look normal. So you can actually do the calculations and you say, well, what's the return time for the crop loss? That is, how many, what's the time between the years where you have a 10% loss in the crop due to temperature variability? Well, the answer today is 1 out of every 32 years, which is why growing up in upstate New York, I never cared about this. But if you just add 2-degree warming to that, the return time is 1 out of almost every year. Almost every year you see that reduction. And more important, if you go to say, what are the odds that you're going to see a 25% reduction? How often will that happen? Well, today it's never. You'd never see that, right? But just with a 2-degree warming, which is 2050, this is 35 years from now. This is not like, sometime in the distant future. Well, for me, it's not, anyway. 35 years from now, you're looking at every 4 years, you're looking at a 25% reduction in loss, right? 25% reduction in yield, just due to temperature effects alone. And then you add on top of that the volatility associated with precipitation, you find out that the crop production in all the breadbasket countries, the US, Europe, Ukraine, what am I missing? I missed one. China, is going to be extremely volatile. Now, what does that mean? It means you're going to have to be moving crops all over the world, to feed people in the mid-latitudes, right? Not to mention the tropics. Yeah. It means in the United States, we have to do farming entirely differently because, I don't know if people know, but there's a food bill, right? And most of the food bill, the farm bill, I should say, the farm bill, most of it's spent on crop insurance, right? And crop insurance today just is buying the cost of drought, right, and floods. Add to that an equal stress due to temperature variability, and you find out you're going from paying $60 billion a year to $120 billion a year, right, in insurance to farmers. It's a lot of money. It's a lot of food. Okay, so you have increased variability in crop production in mid-latitudes, and this is not an end of the century thing. This is like before I die, probably, despite my accident record. Reduced nutritional content. If you grow grains under higher temperature, this is not my specialty. Apparently, the protein content that you measure in wheat and rice goes down. Okay. Now, the reason why that's maybe important is not so much because you get a lot of protein from grains, is because apparently the disease things, stuff like with plant, is highly correlated to the protein content of the plant. Increased disease transmission rates. Higher temperatures, this happens. This is not a surprise. Increased loss of stored water and water stored in snowpack. Important for the Sierra and the Himalaya. Right. By 2050, most of the countries in the subtropics will experience less rainfall. In particular, Northern Africa, Southern Europe, Caribbean, Middle East. And all this also leads to increased frequency, duration, intensity of drought, which I don't have time to go into. Okay. Now, impacts of changing precipitation are in a lot of places where you're on the edge, you have to change your staple crop, right? The duration and intensity of monsoon. It turns out that the probably one place where this is most important is in Indonesia, where the monsoon season today is just long enough to produce 2 crops of rice. If you shorten the monsoon season, you can't fit in the second crop of rice. And so actually the correlation between monsoon season like today and total rice production in Indonesia is something around 0.8. You know, it's basically if you know the onset time of monsoon, you know how much rice is produced by the country. The climate change scenario reduced the monsoon season length from anywhere between 10 days shorter and 30 days shorter. So you don't grow 2 cups of rice in Indonesia. That's a lot of loss of food. Rice is a staple crop in Indonesia, which is the 4th most populated country in the world. Increasing the flooding in mid-latitudes and the tropics, that increases the, that is an increase of the intensity of precipitation. More water vapor in the atmosphere, and this means you have more intense precipitation on average. On dry soils, this is not good because it causes a leaching of the soils, nutrients in the soils. Okay. Increased carbon dioxide in plants. For C3 plants, carbon dioxide is a limiting nutrient, but the benefits of this actually really been downplayed from the original studies to now it's actually a really small effect. If you include the effect of changing temperature due to CO2, you find out that pretty much everywhere, very quickly, the net effect of the climate changes is way outweighs the effect of increasing carbon dioxide as a food, right? Effects on soil biogeochemistry. As you increase temperature, I think this is probably one of the topics of last week's talk, is you increase temperature, you just reduce the organic content of the soil, that's the food, that's the nutrient supply for the plants. And I already mentioned the effects on plant pathology. It's more susceptible to disease, okay? You have a sea level rise of 35 centimeters, probably a pretty reasonable estimate. That's mostly just due to the fact that you heat water, it expands, and it's got to go somewhere, and it goes up. When that happens, you push more salt water into the land, and you tend to salinize the groundwater, which is not good for growing crops, okay? So changes in pests and pathogens. I'm going to skip the details here and just point out that if you look at the numbers, just due to the temperature effects alone, you expect about a doubling of the pest pressure in the world. That is, the pests will eat about twice as much as they do today. Now that means you go from sort of a 6 to 10% loss per year due to the pests to, you know, about a 12 to 20% loss in the mid-latitudes. And the only way to keep up with that is to increase the pesticide use, right? So it's not so much, you know, if you figure it out, for the United States, it's a loss of about $6 billion a year. But that's not the big deal. It's probably that you have to double the use of pesticides, right, to keep up with the pest pressure. And it's simply because pests are cold-blooded animals. You increase their temperature, metabolism goes up, and they have to do something. So what do? They eat more. Right? It's a really basic thing. So I'm going to skip all this. If anyone's interested, I can show you the pictures. Summary. Say by 2100, growing season temperatures will very likely exceed the highest temperature on record throughout the tropics and subtropics. That'll imply a 20% to 40% reduction in the yields of the major crops due to temperature changes alone. Okay, if you add on top of that the precipitation changes in soil geochemistry, they all have the same sign. That is, we can't quantify what the effect is going to be, but they all reduce yields more. They just add to that effect, right? Increased volatility in crop yields in the mid-latitudes, in the breadbasket countries. In the tropics and subtropics, crops will be further stressed by reduced rainfall. Increased CO2 fertilization effect is small, less than 10% for a CO2 doubling is what the current literature says. So these are really small positive feedbacks due to increasing CO2 compared to the negative sides of the temperature changes. And pests and pathogens losses double. So let's go back to this slide I showed you at the beginning. Where do the food insecure live? Well, they live in places where you're already beyond the optimal temperature. Increasing temperature is just going to reduce the yield, right? It's also the place where that 2.5 billion people are going to be added, right? They're all added in those countries. They're not added to the United States. Almost all those 2.5 billion people get added to these places. These are the places where they are developing countries today. Agriculture is the big thing in most of these countries, except China, right? And they're places where agriculture is going to be stressed the most, right? The estimates are very crude that you have 200 to 400 million more people at risk of food hunger by 2080, right? Now, this is always a downer, so I'm going to tell you a few things that I think are optimistic on this. One is there is a possibility that you can avoid this scenario. That one possibility is you can genetically modify the crops so that they stay on the optimal. As you warm the temperature, you keep the crops so that the optimal temperature is going to higher and higher, right? My understanding, talking to the breeders, well, first of all, my surprise, they've known about the temperature effect for 30 years and they've been working on it. They've made no progress in 30 years. Okay, so that's one thing you could do, but heat apparently is a very complex trait to breed for, and there hasn't been any progress there. You could switch things you're growing. Millet and sorghum grow really well under high temperatures. But if you look at places that grow millet and sorghum today, they're actually switching away from that and growing maize. And the reason is in part because of cultural. It's seen to be, you're rich if you can grow corn. And in part because millet and sorghum are both extremely difficult things to mill and process. So that's actually not happening. The other thing you can do is not go to 3 times CO2. And to be perfectly honest, we don't have to do that. I mean, it's a huge reduction in CO2, but there are technologies out there that can really cut those emissions down a lot. I think what we're missing is, I heard a talk once by Thomas Friedman. I think it's Thomas Friedman. He's the columnist for New York Times, I guess. And he said there are 3 things that have to happen if you're going to solve a really big problem. One is you have to be honest with the people about how big the problem is. And I've tried to be honest today with what the climate change is going to be and what the implications for food production are going to be. The second is you have to offer a solution that addresses the whole problem, not just, oh, this is going to be a little, I can do a little bit, I can turn off the lights, that'll help a little bit, but it doesn't solve the problem. It's really, like I said, you have to get the emissions down to only 2% of today's emissions. But the third thing you have to do, which nobody has done yet, is to lay out why that world would be a better world for you, right? And I do think you can actually envision that world and why it would be maybe a world would be better if you didn't have inversions with pollutions in it every other day in the wintertime here. You know, it's not hard to do this, right? But no one's doing that. And I think that's where you can do a lot to actually avoid the world that is painted by this talk, for example. Okay, well, thank you very much for your attention and for inviting me down.